Alright, welcome back to the last section of Chapter 3. So we're talking about permutations and combinations in Section 3.7. So permutations and combinations are related to what we call counting problems or counting strategies. And it's not quite as simple as you might think it is when you hear counting, right? You might think, well, just 1, 2, 3, 4, 5. But in essence, that's kind of what we're doing, just on a larger scale. So permutations and combinations are going to allow us to count out total numbers of possibilities of certain events. And this is going to be related to probabilities because in probabilities we look at the number of occurrences of an event divided by the total number of possible outcomes. And these tools that we're going to get in this section help us count those out when we're dealing with larger sets of data, larger numbers, so we don't have to do it by hand. Okay, so let's look at this first example. So let's take a small menu of items, 3 appetizers and 2 desserts. If you can choose exactly one of each, how many different possibilities do you have? Okay, so there are 3 appetizers and 2 desserts. So I can choose exactly one of each. So let's go ahead and list these out. So I could choose the first appetizer with the first dessert. I could choose the first appetizer with the second dessert. I could choose the second appetizer with the first dessert, or the second appetizer with the second dessert. Whoops, these are supposed to be D. Alright, with the second dessert, or I could choose the third appetizer with the first dessert, or third appetizer with the second dessert. Okay, which means we have 6 possibilities. Alright, so 6 possibilities in this scenario. So suppose, in this basic counting rule, suppose that there are m choices for the first category, n choices for the second category, p choices for the third, and so on. The total number of available choices is just going to be the product of all these values. So m times n times p times etc., etc. This is called the multiplication rule for probabilities. So if we go back and look at this example again, but let's step it up a little bit more. Suppose at a particular restaurant you have 8 choices for an appetizer, 11 choices for a main course, and 5 choices for dessert. If you are allowed to choose exactly one item from each category for your meal, how many different meal options do you have? So what we would have had to do before, using this method up here, was we would have had to say, okay, I have 8 appetizer choices, 11 entree choices, 5 dessert choices. So I would go appetizer 1 with main course 1 with dessert 1. Appetizer 1 with main course 1 with dessert 2. And we'd have to go and literally list out every single possibility. That is not a good use of our time. Instead, I can say, well, there are 8 choices for my apps, 11 choices for the meal, and 5 choices for dessert. 8 times 11 times 5. There are 440 options. So we have 440 options in this case, right? And like for the first example we did, we had 3 and 2. 3 times 2 gives us the 6. Right, on a smaller scale there. But obviously, writing out all 440 choices is not practical. So using this method can really speed up this process of counting. Next up, there are 21 novels and 18 volumes of poetry on a reading list for a college English course. How many different ways can a student select one novel and 1 volume of poetry to read during the quarter? So they have 21 novels to choose from, 18 volumes of poetry. They want to choose one of each. So there are 21 novels that they are going to choose from, and there are 18 volumes of poetry to choose from. There are 378 ways that they could choose one of each to read during the quarter. Right? 378 ways that they could choose one of each to read during the quarter. So now let's start talking about some of this terminology here. So we're going to look first at permutations. So, first question, how many different ways can the letters of the word math be rearranged to form a 4-letter code word without using one letter more than once? Okay, so if we were going to do this by hand, we would have to, write out, so there's M-A-T-H, and then we start mixing up the letters. Right, and just keep doing that and keep listing them out. But again, not practical, and it's very easy to miss something if you don't do it very methodically. So instead, we're looking at the number of choices we have in order to make each of these decisions. So I'm going to put in 4 placeholders, 1 for each letter. So we're making a 4-letter code. So I'm going to place the first letter. How many choices do I have of letters that I could put there? Well, there's an M, an A, a T, and an H. I have 4 choices for this first one. Now I'm going to place the second letter. I've already taken one of the letters for the first slot. That means there are now only 3 letters left, okay, for the second slot. Now for the third one, I've already taken 2 letters. There's only 2 left for the third slot. And in the last slot, well, I've already used 3 out of the 4 letters. There's only 1 letter left to choose from. So there's basically no choice on that last one. Each of these choices then gets multiplied using that multiplication rule. 4 times 3 times 2 times 1. There are 24 ways of creating a 4-letter code without using any of the letters more than once. Now, this process for coming up with numbers of choices comes up so frequently we have special notation for it. This is called a factorial. So the factorial symbol looks like an exclamation point, and it's defined as follows. If we have n factorial, that's going to be n times n minus 1 times n minus 2 times n minus 3, etc., all the way down to 1. So basically, whatever positive integer n is, you multiply that number times every number that came before it, all the way down to 1. Okay, with a couple of special notes here. 1 factorial is just 1, and 0 factorial is also 1. Okay. So let's look at an example. How many ways can 5 different door prizes be distributed among 5 people? Okay. So I have 5 people that I'm giving door prizes to, and there are 5 door prizes. So I'm going to give one to the first person. I have 5 choices of which door prize to give them. The next person, I have 4 left to choose from, then 3 left, then 2 left, then 1 left to choose from. This is the same thing as 5 factorial. Okay, 5 factorial is 5 times 4 times 3 times 2 times 1. This is 120 ways of giving those 5 different door prizes to 5 different people. Okay. Then we have 8 sprinters have made it to the Olympic finals in the 100-meter race. In how many different ways can the gold, silver, and bronze medals be awarded? So this one's a little different because now I have 8 racers, but I'm only giving away 3 medals. So that means I have 1 medal, 2 medals, 3 medals. Okay. How many choices do I have for the person getting the gold medal? Okay. Well, there are 8 people, so there's a possibility of any of the 8 getting that medal. Okay. Once that medal has been given out, the number of people left to receive the silver medal, there's only 7 of them left. And then once I've given out gold and silver, there are 6 people left who could potentially win the bronze. Okay. So that gives us 8 times 7 times 6, which is 336 ways of giving out the gold, silver, and bronze medals. Okay. So in this case, we didn't take 8 factorial, right? 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We didn't do all that because not each racer is going to get a medal. Only the first 3 are. So we end up getting rid of all the other values besides those first 3. Okay? And this process is what we're going to look at through the lens of a permutation. So, if R items are selected from n choices without replacement, we call this ordered arrangement a permutation, where this is defined as NPR equals n factorial over n minus r factorial. Okay, n factorial over n minus r factorial. So if we go back and look at this example again, we had 8 racers, 3 medals. So I'm choosing, right, so again for this example, I have 8 racers, and then I'm choosing 3 medal winners. That would be permutation of 8 with 3. Okay, 8 choose 3. So that's 8 factorial over 8 minus 3 factorial. So that's 8 factorial over 5 factorial. And then let me finish this up here. So that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. We get a bunch of cancellation, right? There's a 5 and a 5, a 4 with a 4, 3 and 3, 2 and 2, 1 and 1. And all we're left with is 8 times 7 times 6, which is what we have right there. Okay, so in some cases we can justify it just using, right, kind of these slots, those placeholders, but sometimes it gets a little more complicated. We need to utilize this formula. Okay, so a few notes with permutations here I want to highlight. In the case of permutation, order matters. Okay, the way that I like to think about this is labeling matters. Okay. So they say order matters because they talk about the example with first, second, and third place, right? Giving a gold medal to someone is different than giving a silver medal to someone, right? The order they're chosen matters. Okay, and I just say that the labeling matters. Okay, if I give one person gold and one person silver, they can tell the difference. If I'm just giving out, participation medals to everyone, it doesn't matter which one you get because they're all the same. Okay, so that wouldn't be a permutation. Permutation, the labels are distinct. Okay, so I'll say distinct labeling matters. And selections are chosen without replacement. Okay, so we're not putting back anything that we take out. This shows the process. You can do permutations and combinations on your calculators, your TI 8384. You can also do them on scientific calculators as well. I'm going to show you in a little bit how I do them on Desmos. So let's look at this example. In how many ways can a 1,000-person marathon finish first, second, and last? So a 1,000-person marathon, first, second, and last. Okay, so this is going to be a permutation because, again, those labels are distinct from each other, right? A person coming in first is very different from a person coming in last. So this is going to be a permutation where I'm taking 1,000 people and I'm choosing 3 of them to label, right? First, second, and last. So that's going to be 1,000 factorial over 1,000 minus 3 factorial. So that's 1,000 factorial over 997 factorial. Now one trick we can do, we saw in the last one, I just wrote out all of the terms in the factorial and then canceled them. That's not so practical in this case. You can't write out 1,000 terms in the top and 997 terms in the bottom. Instead, what we can do is I can start at 1,000, so 1,000 times 999 times 998, and now when I get to 997, I'm going to just write it 997 factorial, because this number includes all the other numbers that come after it. Okay? And down here, I still leave 997 factorial. Okay, now I just want to be clear, this is not just the number 997. Okay, this is 997 factorial, so it includes 996, 995, 994, all the way down to 1 are included in those. So instead of writing them out, I'm just leaving it in factorial form. This is the same in the top and bottom, so those actually cancel out. And that simplifies our work immensely. All we're left with is 1,000 times 999 times 998, which is already a huge number. It's 997,002,000, and that's it. So 997,002,000 different ways that we could have a marathon with a first, second, and last place racer. Okay. Let's look at the next example. How many 5-character passwords can be made using the letters A through Z if repetition of letters are allowed? What about if repetition of letters is not allowed? What is the difference between these two scenarios? Okay, so we have two cases here. Let me just type this. So what if we have repetition allowed? And then repetition not allowed. So we're creating a password with 5 letters in it, and we can repeat. Okay? So if repetition is allowed, that means for the first letter, I have 26 choices, right? Any letter in the alphabet. The second letter, because I could repeat the first letter, I still have 26 choices. Third one, 26 choices, 26 choices, 26 choices. So that means I have 26 to the 5th power number of choices. Okay? Because I can choose any letter I want for any of these. And that number is 11,881,376. But if repetition is not allowed, then my first letter I pick, I have 26 choices. The next one, however, I can't use that same letter, so I only have 25 choices. I can't use either of those two for the next one, so it's down to 24, then 23, then 22. Okay. This is a permutation of 26 choose 5. Out of 26 letters, I'm choosing 5 of them distinctly to make this passcode. And that value is 7,893,600. So, by saying I can't reuse letters, we have lowered the number of possible combinations by about 4 million, right? About 4 million fewer choices here because we're not allowing repetition of letters. All right. So that brings us to the next major term, and that is combinations. So if R items are selected from n choices without replacement, we call this arrangement a combination, where we have NCR or CNR, depending on how you read it, is n factorial over r factorial times n minus r factorial. Now, what distinguishes a combination from a permutation? Well, primarily, it's that order doesn't matter, or we have no distinct labels. Okay. And then, of course, selections are chosen without replacement. But the big difference between a permutation and a permutation, the label that I give matters. In this case, the labels don't matter. So like I mentioned with the example with the race, if I'm giving a medal for gold, silver, and bronze, those are distinguishable. They're different from each other, so it matters which one you get. If I'm giving away a participation medal to everybody, then it doesn't matter which one you get because they're all the same. Okay? They are not distinct from each other. Okay? So the order I give them doesn't matter. Okay? So in this case, notice we're taking n factorial, so that would have been the permutation by itself, but now we're also dividing by r factorial. And what that's doing is it's essentially getting rid of that ordering, right? Where the permutations have distinct labels, they have an order to them. Combinations don't, so we're dividing away that order, okay, and leaving it kind of orderless or not distinct. So let's look at this example. United States Senate Appropriations Committee consists of 29 members. The Defense Subcommittee of Appropriations Committee consists of 19 members. Disregarding party affiliation or any special seats on the subcommittee, how many different 19-member subcommittees may be chosen from among the 29 senators on the Appropriations Committee? So in this case, the first thing to recognize, so we have 29 members of the Appropriations Committee, and we want to form a subcommittee of 19 members. Okay. The first question is there a rank? Is there an order or a label to provide to these subcommittee members other than, member? And there's not. Okay, so whether I'm the first member chosen or the 19th member chosen, I'm still just a member. Okay, so this one is going to be a combination, because that order, that labeling doesn't matter. So it's a combination. Out of the 29 members, we're choosing 19 of them. Okay. So this gives us 29 factorial over 19 factorial, 19 factorial times 29 minus 19 factorial. Okay, which is 29 factorial over 19 factorial times 10 factorial. So simplifying this is a little bit tougher, but we're going to go 29, 28, all the way down 20 times 19 factorial. So I'm going to stop at 19 factorial because that's the first thing that I'm going to be able to cancel now, because I have a 19 factorial in the numerator and one in the denominator. So those cancel. And then let's write out what we have left. So we have 29, 28, 27, 26, 25, 24, 23, 22, 21, 20 over 10 factorial, which is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And now our job would be to cancel whatever we can. Okay, so we can go through this quickly. 10 and 2 is 20. 7 and 3 is 21. What else do we have? 4 and 6 is 24. Right, 5 cancels out with part of the 25. 9 will cancel out with part of the 27. Okay, and then the 8 has like a 4 and a 2 in it, so you can go through and cancel that one as well. But bottom line, when you do the simplifications, you'll still have to run it through a calculator because it's a huge number. We get 20,030,010. 20,030,010. number of ways we could create a 19-member subcommittee from those 29 senators. Okay. So as you can see, when the numbers get a little more disparate like this, it can get pretty messy. I do want to show you on Desmos how you can do this. So you can either find the function on Desmos or just type it in. But if we go to Functions, go to Stats, and you'll see down here we've got NCR and we've got NPR down here. So it does both combinations and permutations in Desmos. So I'm going to click NCR. And if you go to this, it tells you it requires 2 arguments. So I'm going to need the N and the R. In this example, N was 29 and R was 19. And there we have it, 20,030,010. Okay. If we wanted to look at the permutation, right, I can just type NPR, and then it recognizes that instantly, so 29 and 19. So if the order mattered, oof, that would be a huge number. Right, if each person had a different title, then that would be a ridiculously high number of different ways to organize them. Okay. It can also do factorials. So, right, when we set that up, we had 29 factorial over 19 factorial times 10 factorial. So I can do 29 and just go in and find the exclamation point. It recognizes that as a factorial over 19 factorial times 10 factorial. And there you have it. You get the same value using the factorials instead of using the combination notation. Okay? But those are both ways that we can do that using the technology instead. All right. Next up, we have probability using permutations and combinations. So we not only want to look at how to count them, but also how we can use this in a probability. So for this first example, a 4-digit PIN number is selected. What is the probability that there are no repeated digits? Okay, so the probability of no repeated digits that's going to be the number of pins in the event, right, the event in question, over the total number of possible pins that are out there. Okay, so let me just put this in text. So our numerator is going to be the number of pins with no repeated digits over the total number of pins. And that is a fraction. So the number of pins with no repeated digits over the total number of pins. Okay. So if we're looking for number of pins with no repeats, well, that's going to be a permutation with, out of the 10 possible numbers, 0 through 9, I'm choosing 4 of them without repeating to make this pin. Okay. And then the total number of pins, well, the first digit of the pin, I have 10 choices of numbers. Second digit, I have 10 choices, then 10 choices, then 10 choices. So this is going to be 10 to the 4th. That's the total number of possible pins we could have. Okay. So this 10 permutation choosing 4, that's going to be 10 factorial over 6 factorial over 10 to the 4th. Okay. 10 factorial over 6 factorial is going to be 10 times 9 times 8 times 7, because the 6 factorial that you would get next would cancel with the 1 in the bottom. So that's gone. Over 10 to the 4th, which is 10 times 10 times 10 times 10. You get one cancellation in the tens, and we're left with 504 over 1,000, which as a decimal is 0.504. So if we're choosing a 4-digit PIN number, the probability that there are no repeated digits is 0.504. So there's about a 50-50 chance that you get no repeated digits in this 4-digit PIN number. Okay. Going back to our playing cards, Bucky told Satchel he would give him a big hug if he drew 3 aces and 2 5s in no particular order. What is the probability Satchel draws this 5-card set? So we're looking for the probability that Satchel draws 3 aces and 2 5s. So this is an AND probability, okay, and these are independent events, right, because there's no way to draw an ace and a 5 in the same draw. So this is just going to be probability of getting 3 aces times probability of getting 2 5s. Alright, so probability of getting 3 aces, that's going to be a combination. And the reason is because it doesn't matter which aces I get, okay? Because you could get ace of hearts, diamonds, spades, or clubs, and it wouldn't matter. Okay, so I could get these 3. I could get, I could get those 3. I could get these 3. It doesn't matter which ones I get. It just matters that it's an ace. So it is a combination. Of the 4 aces, I'm choosing 3 of them out of the total number of ways. Let me actually fix this. We're going to multiply by the probability of the 5s first. So we get, out of the 4 5s that are in the deck, I'm choosing 2 of them. Okay, so again, this is choosing 3 of the 4 aces, choosing 2 out of the 4 5s, over the number of ways that I can choose 5 cards out of the entire 52 card deck. So again, a probability is the event over the total, right? The total sample space. So this is the number of ways I can get 3 aces and 2 5s over the total number of ways I can get 5 cards out of the deck. So, this, if we simplify, would work down to 24 over 2,598,960, or as a decimal, is 0.0000923. So what is the likelihood that in 5 cards he's going to get 3 aces and 2 5s? Extremely unlikely. Extremely unlikely, right? There's only 24 ways that could happen out of 2.5 million possible draws for those 5 cards. Okay. And these types of probabilities are what casinos feed off of, right? The idea that the odds of you getting a particular set of cards is very low, so in terms of betting, right, they're going to win most of the time because the odds are in their favor that you won't get a particular string of cards. Okay? And then, those few times that you do beat the odds, that's when you get your payouts. Okay. Speaking of gambling a little bit, in a certain state's lottery, 48 balls numbered 1 through 48 are placed in a machine, and 6 of them are drawn at random. If the 6 numbers match the numbers that a player had chosen, the player wins $1 million. In this lottery, the order in which the numbers are drawn doesn't matter. What is the probability of winning the $1 million prize if a single lottery ticket is purchased? So we're looking for the probability that all 6 numbers that I have match the numbers that they draw. Okay. How many ways are there for me to match them? Well, only one, because I only bought one lottery ticket. Okay, I bought one lottery ticket. Now, how many different combinations of 6 numbers are there? Well, there are 48 numbers to choose from, and they're picking 6 of them. So, this is 1 over 12,271,512, which as a decimal is approximately 0.000000815. So if you're wondering how likely you are to win the lottery, it's even less likely than drawing those 5 cards in that card example from before. Okay, so if you consider a percentage, we'd multiply this by 100. It would be right there. So this is 0.00008% of a chance of winning that $1 million. Okay, so very, very unlikely. But now, in the state lottery, from the previous example, if 5 of the 6 numbers drawn match the numbers that a player has chosen, the player wins a second prize of $1,000. What is the probability of winning the second prize? So the probability that 5 of 6 of the numbers match. Okay, well, this would be, first of all, I need to choose my 5 winning numbers. So of the 6 winning numbers, I would have to choose 5 of them for this to happen. Okay, again, of the 6 winning numbers, I would have to choose 5 to get second prize. And then because I didn't win first prize, that means out of the other 42 numbers, I would have to choose 1 of them. Okay, so again, I want 5 of 6 to match, which means of the 6 matching numbers, I would choose 5, and of the 42 other non-matching numbers, I would choose 1. And that gives us our 2 combinations, and then of course divided by the total number of ways to choose 6 numbers out of the 48. And this is 252 out of that 12 million number, 12,271,512. Which is approximately 0.0000205. So, it is significantly more likely than winning the $1 million, however, still very, very incredibly unlikely. So, you have gone from 1 out of 12 million chance to a 252 out of 12 million chance of getting 5 of the 6 matching numbers. Okay, so bottom line, winning the lottery, as you probably already knew, very unlikely. And then we come to our last example here, the birthday problem. So suppose 10 people are in a room. What is the probability that there is at least one shared birthday among these 10 people? So this problem is very interesting. We like sharing it just because it seems almost counterintuitive. You think, well, if I'm in a room with 9 other people, and there's 365 days in the year, the odds of us having a matching birthday in the room must be so incredibly small, right? Like, what are the odds? Well, it turns out it's not as unlikely as you might think. So the probability of at least one shared birthday, this is another one of those at least one problems. So we're going to do 1 minus the probability of none shared. Okay. Okay, so 1 minus. If we're saying that no one out of the 10 people shares a birthday, and how many different ways can we do that? Well, this would be a permutation because each date is distinct. Out of the 365 days, I would have to pick 10 different days for them to not be shared. And then now the question is, how many different possible birthdays are there? Well, there's 365 birthdays possible for 10 people. So we divide by 365 to the 10th power. Okay, so that's just 365 times 365, right? 10 times. Right? That's the first person's birthday, there's 365 choices. Second person's birthday, 365 choices, etc., etc. So we set this up, and I'm going to go ahead and do this one on Desmos so you can see it. See it in action here. So we get 1 minus permutation of 365 choosing 10 over 365 to the 10th power. And we get approximately 0.117, roughly. So 0.117. So what does this tell us? This tells us that if we're in a room of 10 people, the probability that at least two of those people will share a birthday is 0.117. So almost 12% chance that you will share a birthday with someone else in that room, which, if you think about it, seems really high. Right? It seems a little counterintuitive, and if you get more people in that room, that probability is just going to go up and up until you get to extremely likely that you would share a birthday with someone else in that room. So, and that actually brings us to the end of Chapter 3. So great job making it through this chapter, dealing with lots of probabilities, lots of different counting strategies, different ways that we can solve these types of problems. So when we talk next time, we'll be looking, starting into chapter